This is time, and now we are here. In fact, we're always here. We're always in the present. Everything is always in the present. The past no longer exists, and the future doesn't exist yet. It makes no sense if I ask you, can you touch an object that belongs to the past or the future? Because everything that exists only exists in the present. But let me be very clear right off the bat. I am not talking about seeing an object as it used to be in the past. Like, for example, we can observe a star which is 10 light years from us, so we see it today as it was 10 years ago, not as it is now, because its light took 10 years to reach us. It's equivalent to seeing a 10-year-old photograph. The picture representing the object is 10 years old, but the object itself has also aged 10 years, it's not 10 years in the past. No, I'm talking about actually being physically present in the same room, touching an object that belongs to the past. Well, you can't, can you? Because the past no longer exists. So, if you can touch the object that is right here in front of you, it's in the present, currently with you at the same moment.
Or is it?
Einstein's general relativity explains that time and space are inextricably linked. You are constantly traveling through space and/or time. Let's diagram it like this. Let's put the time velocity axis horizontally and the space velocity axis vertically. When you sit still, you don't move in space, but you move in time. You travel through time at the speed of 1 second per second. Your movement arrow is therefore completely horizontal. The spatial speed is 0, since you are not moving, and the temporal speed component is maximum. But if you start walking, if you start moving through space, the theory of general relativity explains that, therefore, you slow down in time. The faster you move in space, i.e. the larger the spatial velocity component, the smaller the temporal velocity component. A famous thought experiment performed by Einstein involved twins. One twin stays on Earth, while the other traveled for, say, 20 years, very fast at a good fraction of the speed of light, and then 20 years in the other direction, back to Earth. The twin who stayed on Earth aged 40 years, but the one who traveled only aged 10 years, because the high speed caused time on a spaceship to slow down. So this is the general idea. Of course, the effect on time, the time dilation that we experience on a daily basis in our lives is completely negligible, and we absolutely don't feel it. It's only starting to be sensitive at enormous speeds. And by enormous, I mean much faster than the fastest man-made object, at speeds that are a good fraction of the speed of light. But it is nevertheless a real effect, and measurable. In order to prove Einstein's theory and its predictions, in 1971, two physicists, Joseph Hager and Richard Keating, carried out an experiment using atomic clocks. Atomic clocks are incredibly precise clocks based on perfectly regular atomic oscillations. They generally use cesium atoms, whose frequency is exactly 9,192,631,770 oscillations per second. Thus, atomic clocks are accurate to almost a 10 billionth of a second, or a hundredth of a nanosecond. The experiment basically consisted of putting 4 of these clocks on a plane, just to be sure, flying around the world, and then comparing the time displayed on them with similar clocks that stayed on the ground at the Naval Observatory of the United States. And indeed, the experiment confirmed Einstein's general theory of relativity. The clocks that flew were slightly behind those that remained on the ground. They were about 59 nanoseconds late. Granted, it's a really short time, it's 0.000000059 seconds. But it's still 600 times longer than the precision of these clocks. So for an atomic clock, it's a fairly long duration. So it's great. We managed to prove experimentally and undeniably that time does indeed slow down when something's moving very quickly. But then a thought struck me. As the plane took off and gained speed, time began to slow down for the clocks. Throughout the flight, they moved through time at a different speed than the rest of the world. When the experiment ended and the plane landed, the passage of time stopped being slowed down and resumed at a normal pace. But wouldn't that place the clocks in the past? When And how did those clocks return to the present with us? Well, that's the thing. They didn't. How would they have done it? What phenomenon would make them jump 59 nanoseconds into the future in order to catch up with the rest of the world and return with us to the present? They have not returned to the present. They remained in the past. They belong to the past. And here's the proof. The time written on them is exact. The experiment did not disrupt the clocks. They're not disturbed. They're not late. The time written on them is still correct. It is the exact time these clocks are at. It's literally written on them that they are in the past. You can see them, you can touch them, like normal clocks, like normal objects, but they are 59 nanoseconds in the past. Besides, they are in the past relative to you, which means you are in their future. You are 59 nanoseconds in the future for these clocks, and for the plane that transported them. The same time dilation that the clocks were subjected to also applied to the entire plane and its passengers. Everyone who was on the plane during the experiment then found themselves 59 nanoseconds in the past. And for them, the rest of the world is 59 nanoseconds in the future. All it took to send objects and people into the past was a simple commercial flight. Every time you fly, your passage of time slows down ever so slightly compared to the rest of the world on the ground. When you land, you have traveled thousands of miles through space, but you have also been shifted a few nanoseconds in time. And yet, you can clearly see the people who come to greet you at the airport, and the airport itself, and the rest of the world. It's all in the future relative to you, and you're in the past relative to them. But it all works really well and feels like the present. Every time you walk, every time you drive, every time you fly, you are traveling in space, but you are also shifted just a little bit in time. With every journey you take, time slows down for you. This means that each of us lives in our own present, our own now, which is slightly different from everyone else's, because since we were born, we have traveled different distances at different speeds than everyone else. This led me to the conclusion that the present as we feel it, i.e. a precise moment, doesn't really exist. We all live at different times. We can perfectly see ourselves, touch each other, touch the things around us, go about our business with people and things that are slightly in the past or in the future in relation to us, but not necessarily exactly in our personal present. If we take the example of the Einstein's twins from earlier, and we say that the experiment began in 2000, the ship one of the twins is on takes off, and since it goes really fast, time slows down a lot on board. After 20 years, it has to turn around, but it's 20 years on Earth. It's 2020 on Earth. On the ship, only 5 years have passed, and the clock on board reads 2005. For them, they turn around in 2005. Then they come back to Earth. They arrive in 2040 on Earth. But for them, it has really only been 10 years. They are in 2010. They are really physically in 2010. Which absolutely doesn't prevent the traveling twin from finding the one who remained on Earth, from hugging each other and telling each other about their lives. And yet, they are spaced 30 years apart in time. The twin who traveled is effectively 30 years in the past compared to the one who stayed on Earth. And it's not over yet. The Earth orbits the Sun at approximately 107,000 kilometers per hour. This is obviously much faster than a plane. About 120 times faster. This means that time on Earth passes slightly slower than on the Sun. Let's risk a crude calculation. Since the atomic clocks have been shifted by 59 nanoseconds in 24 hours, the entire Earth, which is going 120 times faster, is shifted by 120 times more every day. We can therefore approximately estimate that each day our planet is shifted by 7 microseconds in the past relative to the Sun, and that for 4.5 billion years. But time also slows down in the presence of strong gravity. This too was predicted by Einstein's theory of general relativity. the stronger the gravity, the more time slows down. So there are, at least, two things that slow time down: speed and gravity. The proof that gravity also influences time is that we must adjust satellites, notably GPS satellites, to the speed of time which passes on the ground, not to the speed of time which flows where the satellites are, in space. Since they are a little further away from the Earth, up there's a little less gravity. And if we didn't adjust that time, the GPS would gradually go wrong. So that too is a real, very measurable effect that has a real impact, in this instance, in our lives. For satellites, time slows down less than on Earth, so they move away, little by little, into our future, or we move into their past. It's the same. Where it becomes spectacular is when we look for extreme gravities, so neutron stars or straight out black holes. And here, if you've seen the film Interstellar, you know what I'm talking about. As a result, the Sun also sees its own time slow down, due to its own gravity, which is much more intense than that of the Earth. The Earth sees its time slow down by its speed around the Sun and also by its own gravity. But it's nothing compared to that of the Sun. The gravity of the Sun is 28 times more intense. We would weigh 28 times heavier on the surface of the Sun, but not at its center, mind you, where the gravity is almost zero. Yes, the gravity at the center of celestial bodies is almost zero, because as we are at the center, all the mass surrounds us, so it pulls in all directions at the same time and it cancels out. So, since there is less gravity, time flows faster, or less slowly, at the center of the stars than at their surface. Anyway, all this to say that time never passes at the same speed everywhere. Everything shifts, everything drifts in time, all things in relation to each other, because of the speed and or because of gravity. And it's still not over. We're going to go even further. After extreme gravity, let's move on to extreme speeds and consider the case of a photon, a grain of light. A photon, since it's massless, always moves at the maximum possible speed, the speed of causality, but since light also travels at this speed, we usually call it the speed of light. At this speed, the spatial component is maximum, you can't go any faster, and the temporal component is zero. Yes, that's right, completely null, which means that photons do not experience time at all. They may travel for years from our perspective, for thousands or millions of years, but for them, from their perspective, the journey will always be instantaneous. From the moment the photons are emitted, time never starts to tick. In other words, photons don't age. When a photon is emitted by the Sun, it takes about 8 minutes to reach the Earth. For us, 8 minutes have passed, but for the photon, time is completely still and never started to pass. It is therefore blocked at this precise moment. If it takes 8 minutes to reach us, but their age is 0, then, logically, they are necessarily 8 minutes in the past. All the light that reaches Earth from the Sun is 8 minutes in the past. And yet, we can perfectly see it and interact with it, even though we are spaced 8 minutes apart in time, even though we are 8 minutes into the future of these photons. Similarly, the light reaching Earth from a star 10,000 light years away is not 10,000 years old. It is 0 years, 0 second old, but is 10,000 years in the past. A photon which was emitted during the Big Bang itself, and which has since traveled through space, has remained stuck in time at time 0. It has not aged since the Big Bang. It has not moved in time since the Big Bang. It's stuck in the past 13.8 billion years ago. And yet, we can see it today. We detect very well the cosmic microwave background radiation, which is a vestige of the time when the universe began. Since photons do not undergo the passage of time, the radiation that we detect is not 13.8 billion years old. It's very young. It's exactly 0 second old. But it is 13.8 billion years in the past relative to us. The photons hitting our instruments are younger than us. They're just 13.8 billion years in the past. And yet, we can detect them, measure them, in something that resembles the present, which seems to us to be the present. objects that are at different points on the timeline interact completely seamlessly and normally with each other. You can perfectly see photons that are billions of years ago, and you can perfectly greet your friend who was just landed at the airport, even though they are a few nanoseconds in the past. I might be a little bit in the past compared to my couch, because I've traveled more than it, but I can still sit on it without falling through it. We generally see, instinctively, the present as one precise moment, without depth, without duration. The past is over and the future is not yet. But this view implies that everything is continually created from the future to become the present, and then is immediately and instantly destroyed into oblivion to become the past? Am I constantly being created from the future, experiencing an instantaneous present, and then immediately being destroyed into nothingness without realizing it? This traditional and intuitive vision of the present, for me, is more difficult to imagine, understand, and explain. A more logical explanation is that nothing is continually created or destroyed, but simply exists somewhere in time. So with the photons of the Big Bang, we have found the lower limit to the present, but is there an upper limit? To find this limit, in theory, we would need something that is very small, so that it has very little gravity, right in the middle of the intergalactic void, and that has not moved since the Big Bang. This hypothetical object would be the most advanced thing in the future in the entire universe. But this limit in the future may not be far away. If this point in time, if this extremity represents a hypothetical object for which time has never slowed down since the beginning of the universe, so it's the one that is the furthest ahead, you can't be further ahead than that. All the other objects for which time has slowed down, either by speed or by gravity, or both, well, they haven't drifted by much. Quite simply because the relativistic effects, the effects of time distortion, are very, very weak. On an airplane, it's of the order of a few nanoseconds per day. It's almost nothing. So everything that has drifted in time, compared to this hypothetical maximum, has not drifted by much, even over billions of years. In the end, it's not that much. And still, it is a limit that we can never reach, because we are already in the past in relation to it, and we can only shift further towards the past. We would have to find a way to travel to the future to reach it. That is to say, have a negative slowing down of the time, an acceleration of time. And even then, the limit could not be crossed, simply because more time does not exist yet. A time machine couldn't travel 1,000,000 years into the future, because this time doesn't exist yet. This time hasn't been created yet. Because time extends. Just as space extends with the expansion of the universe, there is always more and more space, so does time. There is always more and more time. Remember that space and time are linked. They are inseparable. We're talking about space-time. Therefore, it makes sense that time expands just as space expands. And we cannot exceed the limits of time just as we cannot exceed the limits of space. This is time. There you go. I hope this video has shaken your brain as it did mine during its writing and production. I'm very curious to read your reactions and thoughts in the comments. I'm not an expert in astrophysics, so I'm probably wrong somewhere. This is just a thought that I had, which worked on me and which I developed, so I'm really curious to see what you have to say about it. Thank you for watching until the end, and stay curious.